Let's talk about Postgres performance. If you work with Postgres, you've probably written thousands, maybe millions of update statements. But what if I told you that one of the most common operations you run doesn't actually work the way you think it does? And yeah, that misunderstanding, it could be silently killing your database performance.
So let's just start with that one simple question. When you type update and hit enter, what is Postgres really doing under the hood? I can tell you right now, it's not just finding a value and changing it in place. Oh no, the reality is way more complex, and honestly, a lot more interesting.
And that leads us right into what a lot of people call the Postgres update trap. The single most important thing to get your head around is this. Because of how Postgres is built, every single update you perform is, for all intents and purposes, secretly a brand new insert. Let's unpack what that really means. It all comes down to a system called multi-version concurrency control, or MVCC. When you update a row, Postgres doesn't overwrite anything. Instead, it does this three-step dance. First, it just marks the original row as dead. It's not gone, it's just kind of hidden from new transactions. Second, it inserts a completely new version of that row somewhere else in your table. And third, and this is the absolute kicker, it has to update every single index on that table to point to the new row's physical location. So what's the big deal? Well, this process creates two massive problems. The first one is pretty obvious: table bloat. All those dead rows just start piling up, wasting disk space and slowing down scans. But the second one, write amplification, is even more insidious. Think about it. If you have a table with 10 indexes and you update just one little column, Postgres has to do the work of rewriting all 10 of those indexes. That is a huge amount of extra I/O. Okay, so how do we fight this? Our very first strategy is all about giving your data some elbow room. And we're going to do this using a surprisingly simple setting called Fillfactor that can completely change how Postgres handles these updates. You see, by default, Postgres is a bit of a neat freak. It packs your data onto disk pages until they are 100% full. Now that's great for read-only tables, but it's a total disaster for tables with lots of updates. When a page is full, any update forces that new version of the row onto a totally different page, and boom, you trigger that massive write amplification we just talked about. But what if there was space on the same page? Well, that's when a little bit of magic happens. Postgres can perform something called a Heap Only Tuple update, or a hot update, and it's a game changer. If the new row fits on the same page as the old one, Postgres can take a shortcut and avoid updating any of the indexes at all. This is the key to solving our write problem. And the difference is just night and day. Without hot updates, you're writing to your table and every single one of its indexes. With hot updates, you're just writing to the table. That's it. For an update-heavy workload, you could see up to an 80% reduction in I/O. The performance gain is just staggering. So how do you make this happen? It's ridiculously easy. You just set the fill factor for your table. A lower fill factor tells Postgres to leave more empty space on each page, just waiting for updates. So for something like a sessions table, you might go as low as 70. For user profiles, maybe 85 or 90. And you just change it with a simple alter table command. It's one of the most powerful, easy-to-use tuning knobs in all of Postgres. Okay, strategy number 2. I love this one. Instead of using a shotgun to index everything, we're going to become a sniper. We're going to use something called partial indexes to target only the tiny slice of data we actually care about. Let's imagine a classic orders table. It's got millions of rows. But maybe, like this chart shows, 95% of those orders are completed or shipped, and you're never going to query them by status again. All your work, all your queries are focused on that tiny 5% of orders that are still pending. So, why on earth are you paying the storage and performance cost to index all those millions of old rows? The difference in the code is tiny, but the impact is huge. Here's a standard index. It covers all 10 million rows. But look at the partial index. It's got this magical little where clause at the end. Now the index only includes rows with a status is pending. We just went from indexing 10 million rows down to maybe 50,000. And the result is just immense. In a real-world scenario like this, you could see a 97% reduction in the size of your index. And that doesn't just mean it's smaller on disk, it's faster to read and it's dramatically faster to write to, because whenever you update a completed order, Postgres doesn't have to touch this index at all. All right, let's group our final 2 strategies together because they both focus on taking our indexes to the next level, making them even smarter. We'll kick things off with strategy number 3, covering indexes. This is an awesome technique for optimizing your read performance.
Okay, so normally when Postgres uses an index, it's a two-step dance. It finds the entry in the index, and then it has to do a second read to jump over to the main table, what we call the heap, to actually grab the data you want. But with a covering index, you use this include clause to store that extra data right inside the index. This lets Postgres do an index-only scan, answering your entire query without ever touching the main table.
And the performance gain is simple math. You're turning two disk reads into one. You are literally cutting the I/O for that query in half. For your most common, high-frequency queries, this is just a massive win. Now for our fourth and final strategy, and this one is about composite indexes. When you index multiple columns, the order you list them in is absolutely critical. Postgres can only use the index effectively if your where clause uses the columns from left to right. So if your index starts with user ID and then status, a query that only filters by status can't use it. You have to provide that first column, the leftmost one, for the index to kick in.
So, after all that, you've now got this powerful new toolkit for tackling those really tough, high update workloads in Postgres. Let's just do a real quick recap of the 4 big ideas. First, use Fillfactor to leave that elbow room for those game-changing hot updates. Second, use partial indexes and stop wasting resources indexing data you never touch. Third, use covering indexes to slice the I/O in half for your most frequent queries. And fourth, always remember that leftmost prefix rule when you're designing your composite indexes. Okay, so you've done it. You've tuned your tables, you've optimized your indexes, you're fighting back against that nasty MVCC overhead. But there's still one question left hanging. Remember those dead rows from the very beginning? Who actually cleans up that mess? Well, that's a job for a core Postgres process called vacuum. But here's the thing. Its default settings are often way too gentle for demanding high update workloads. So the final question I'm going to leave you with is this. Are you sure? Are you positive you're tuning vacuum correctly? Because if you're not, all that bloat we talked about, it will eventually catch up with you.